Hello everyone, welcome to online session of Maxwell's equation. Myself Dr. Sadanand Kumar, Assistant Professor, Department of Physics, AJ Institute of Engineering and Technology, Mangaluru. And today's session I am going to continue with the Maxwell's equation. The topics for the discussion are Gauss law in magnetic field, Faraday law of electromagnetic induction, continuity equation, Maxwell's Amperes equation, Maxwell's equations in time varying conditions and static fields, finally expression for displacement current. And these informations or these topics in the study material cover under the page numbers 12 to 16. So let us start with the Gauss law of magnetic field. To explain this Gauss law in magnetic field, consider a closed surface of any shape in magnetic field which is shown in the figure. However, surface may or may not enclose the sources of magnetic field such as magnets or current carrying conductor. And the property of the magnetic field that magnetic flux always follows a closed loop. Therefore, a closed surface in magnetic field for every flux line that enters into the surface is equal to flux line emerging out of the surface. Then one can consider the flux over the entire closed surface. The total outward flux is equal to total inward flux. The outward flux is normally taken as positive flux and the inward flux is normally taken as negative flux. Now, the total flux summed over the entire Gaussian surface is 0. This is the Gauss law of electromagnetic. Now, total flux phi can be written as phi is equal to surface integral of vector b dot vector ds, that is equal to 0. That is the mathematical form of the Gauss law for magnetic field. Now, in this expression, the vector b dot vector ds is the flux density over the entire surface. So, this is a magnetic flux. In the previously, we have discussed about the flux lines, that is a maybe electric flux. But when it comes to the magnetic field, it is a magnetic flux over a closed surface, that is equal to 0. That is what the meaning of the statement. Phi is equal to surface integral of vector b dot vector ds is equal to 0, in the sense the magnetic flux over the entire closed surface is equal to 0. Now, using the Gauss divergence theorem, I can write the surface integral can be converted into volume integral, because we have the expression for Gauss divergence theorem saying that the surface integral of vector d ds is equal to volume integral of divergence of vector d dv. That was the expression for Gauss divergence theorem. And same way we can write in this particular discussion the surface integral of vector b dot ds. That means that can be written as in terms of volume integral. That means volume integral of divergence of vector b dv. So, I hope it is clear. The surface integral of b dot ds is equal to volume integral of divergence of a vector field b into dv. Thus, the volume integral of divergence of a vector field b into dv is equal to 0. So, in this expression dv is not equal to 0. Why it is not 0? Because we have considered the elemental volume within the what is the surface volume we have considered for the discussion. Therefore, the divergence of b is equal to 0. If the divergence of b is equal to 0, which means that they form a closed loop. So, magnetic field divergence of magnetic field is 0, in the sense they will form a closed loop. Hence, magnetic fields are said to be solenoidal one. Next topic is Amperes law or Amperes circuital law. Amperes circuital law states that the line integral of the magnetic flux density, that is vector b, over any closed path is equal to product of the current enclosed by the path and the permeability of the medium. Mathematically, one can write the line integral of vector b dot dl is equal to mu I, where vector b is the magnetic flux density and dl is the elemental length, which is equal to mu I, where mu is the permeability of the medium and I is the current. So simply we can say the flux through the elemental length is equal to the product of the permeability of the medium and the current through the elemental length. That is what the expression of Amperes circuital law. Since B is equal to mu H, that's a relation between magnetic field and magnetic flux. Therefore, B is equal to mu H. Therefore, the equation can be rewritten as the line integral of the vector H dot dl is equal to I. So, differential form of the Ampere law can be written as divergence of a vector H is equal to vector J, which means the curling of a vector field in that path is equal to the current density, current flowing per unit area. The next topic is the Faraday law of electromagnetic induction. Now, the Michael Faraday, through its experiments, revealed that when there is a change of magnetic flux linkage in a circuit, EMF will be induced in the circuit. As a result, current flow in the circuit. Also, the current flow sets up the magnetic field. But the another scientist, Lenz, found that the direction of the magnetic field due to current flow, which opposes the change causing it, which means it decreases the magnetic field if the magnetic flux is increasing and increases the magnetic field if the magnetic flux is decreasing. Hence, Lenz stated that the induced EMF is in such a direction as to oppose the change causing it. Now, by considering the interpretations given by the Lenz's interpretations, Faraday defined or stated his statement. The statement of the Faraday law is the magnitude of the induced EMF in a circuit is equal to the rate of change of magnetic flux through it. So, I repeat the very important law it is. Therefore, I repeat the statement of the Faraday law. Faraday law states that the magnitude of the induced EMF in a circuit is equal to rate of change of magnetic flux through it, and its direction opposes the flux changes. Therefore, mathematically we can write induced EMF E is equal to minus dou by dou t of pi, where phi is the flux linkage. Now, for example, if the path is a conducting coil of n numbers, or n number of turns of coils is considered in the conductor, then the EMF induced in the circuit is written as E equal to minus n by dou t of pi, where n is the number of turns in the conducting coil. Now, next concept is the integral form of the Faraday law. To explain the integral form of Faraday law, let me take a loop, which is a closed loop of conducting material, which is stationary. Now, which is subjected to, when it is subjected to change in a magnetic flux linkage, then there is a definitely EMF induced in the loop. Therefore, you can apply the Faraday law in such cases, E equal to minus d phi by dt, where phi is the magnetic flux linkage. This magnetic flux linkage can be showed that the rate of magnetic flux linkage as magnetic flux linkage d by dt of phi as surface integral of dou by dou t of vector b dot vector ds. That is quite obvious. It is a rate of change of magnetic flux linkage. Okay, that can be written as a surface integral of rate of change of the B dot ds, where B dot ds is nothing but the magnetic flux over the elemental surface area. Therefore, instead of phi you can write B dot ds. So the d phi by dt can be written as surface integral of dou by dou t of vector B dot vector ds. But the EMF induced in the loop is E equal to line integral of vector E into dl. That means EMF induced along the length of the conductor or the coil. So that can be written as the line integral of vector E dot vector dl. So in turn we can write the Faraday law in terms of integral form, that is the line integral of vector E dot vector dl is equal to minus the surface integral of dou by dou t of vector B dot vector ds. It is the integral form of Faraday law. Differential form of Faraday law. In order to write the differential form of a Faraday law, it is necessary to consider Stokes' theorem. It states that curl of a vector over a surface is equal to the line integral of vector along the line enclosing the surface. So I have explained about the Stokes' theorem. I gave the statement in mathematical form as well in the previous session, and I mentioned it gives the relation between the surface integral to line integral. Somewhere similar situations we came across here. Now we have to write these Faraday's integral form, Faraday law of integral form in terms of Stokes' theorem. That means the statement of the Stokes' theorem is already stated. Now let me tell the expression for Stokes' theorem, that is surface integral of curling of vector h ds is equal to line integral of vector h dl. That is the equation. In the same format we have to write now this EMF and rate of change of flux. So similar way we can write induced EMF over a closed surface or a closed loop. That means line integral of vector E dot vector dl is equal to surface integral of curl of vector E into ds. Look at the difference. Instead of magnetic flux, now it is electric flux. Therefore, line integral of vector E dl is equal to surface integral of curling of electric vector dot ds. So I have written the Faraday law in terms of Stokes' theorem. Okay, now from the integral form of Faraday law, line integral of vector E dot dl, that is nothing but the EMF induced in the term, that is equal to minus dou by dou t of B dot ds. That's the integral form. Alright, now from the equation number 1 and 2, which means the integral form of the Faraday law is treated as equation number 2, and the one equation we have written in terms of Stokes' theorem, that is line integral of E dot dl is equal to surface integral of curl of a vector E ds is equation number 1. Now from these two expressions, the right hand side terms are compared or equated. Okay, now you write these right hand terms are equal because both of them are representing the surface integrals. So surface integral of curl of a vector E dot ds is equal to minus of surface integral of dou by dou t of vector B dot vector ds. So take the negative term, that means right hand side to the left hand side, it will become plus term. So one equation you will get, that is surface integral of open bracket curl of a vector E plus dou by dou t of vector B is equal to 0. So in this expression we can say either ds equal to 0 or the curl of a vector E plus dou by dou t of B is equal to 0. The ds is not equal to 0 because that is the elemental area which we have considered for the discussion. Therefore there is no chance of taking ds is equal to 0. In other words, the curl of vector E plus dou by dou t of vector B, that can be 0. In other words, curl of vector E is equal to minus dou by dou t of vector B, and this equation is happen to be a differential form of Faraday law. Next concept is continuity equation. Consider a closed surface enclosing the volume of charge density rho, and a closed surface consisting of the elemental small surfaces of area ds. So surface S having a elemental surfaces each of area ds, and algebraic sum of this ds, that means elemental surface, gives rise to the total surface area. Now the charge flow through this elemental surface that can be evaluated as the surface integral of charge flow through the elemental surface area is charge flowing per unit area, that is through that area, that is j dot ds, nothing but current density into ds. So once if you have the charge flow through the small or the elemental area which is j dot ds, you can evaluate the total charge flowing outward from that surface, that is by integrating over the entire surface this j vector j dot vector ds. So that will give the information about the total charge flowing outward the surface. And what is the total charge enclosed by that volume? That can be written in terms of integral form, volume integral of rho dot dv. Now remember, the total charge that is flowing outward in that surface is surface integral of vector j dot vector ds, and the total charge in the entire volume is volume integral of rho dot dv, where rho is the volume charge density and the previous expression j is the current density, dv is the elemental volume and ds is the elemental area. Now as the charge flowing outwards from the surface, then the amount of the charge flowing outward, that must be equal to decrease in the net charge inside the volume. Therefore in terms of mathematics we can write surface integral of vector j dot vector ds, that is equal to minus dou by dou t of volume integral of rho dot vector dv. Now using Gauss theorem, we can write the surface integral of vector j dot vector ds in terms of the volume integrals. So you know the statement of the Gauss divergence theorem that will convert surface integral into volume integral. In other words, surface integral of vector ds is equal to volume integral of divergence of dv. That is the original statement of Gauss divergence theorem. Now in the same format we can write surface integral of j dot ds is equal to volume integral of divergence of vector j dot dv. That is the first expression in the slide, right? Now next step, the volume integral of divergence of j dv, that can be equal to minus dou by dou t of volume integral of rho dot dv. That is from the equation. Which equation? That is the amount of charge flowing outward equal to decreasing in the net charge inside the volume. That is in the previous slide, last equation. Okay, in that jds we have substituted that surface integral of jds as volume integral of divergence of vector j dv. Alright. Now the volume integral of the divergence of vector j dv, that is equal to minus the volume integral of dou by dou t of rho dot dv. So now the both terms are in terms of volume integrals. Therefore I can write divergence of vector j is equal to minus dou by dou t of rho. So this equation is the continuity equation. Next topic is Maxwell's Amperes law. So we have seen the Amperes equation, that is a curl of vector h is equal to j, curling of a vector field that will be results in terms of the current density. That is what the statement given by the Amperes circuital law. Now the Maxwell suggested the corrections to the Amperes circuital law. He has by considering the Amperes circuital law, he has proved the some correction must be necessary in order to complete this expression. So what he has done is he took his expression, and that is curl of H is equal to J, and taking the divergence of that, that means divergence of a curl of H is equal to divergence of J. So divergence of curl of vector H is always equal to 0. Why? Because the curling of a vector, there is no chance of diverging of field of lines or whatever it is. Okay, therefore the divergence of curl of a vector H is equal to 0. In other words, divergence of J is equal to 0. So divergence of vector J is equal to 0. This means that the divergence of current is 0, or there is no net accumulation or loss of charges, which means there are no chance of getting sources or the sinks of current. This is true, which means the equation is true in the case of steady DC currents which are continuous throughout the circuit. Yeah, according to the Maxwell, this equation holds good only for the steady DC currents wherein it is continuous throughout the circuit. However, in a circuit containing a capacitor, normally the AC circuit containing capacitor, during the current starts at positively charged plates, and the charge diminishes as the current flows to the negatively charged plate. So it will accumulate in the negative plates. So here we can think of the condenser plates as sources or sinks of current. So Maxwell concluded that curl of a vector H is equal to vector J is incomplete, and there must be term added to the vector J, so that sum of the two terms gives rise to the zero divergence. Now using the continuity equation, the divergence of vector J is equal to minus dou by dou t of rho, or this divergence of vector J is equal to minus dou by dou t of this rho is nothing but divergence of D, because we have proved that divergence of D is equal to rho V, that is net flux through the surface is equal to volume charge enclosed by the surface. Based on that concept, I can write the rho equal to divergence of vector D, that is equal to minus divergence of dou by dou t of vector D. Now we have got the expression for divergence of J is equal to minus divergence of dou by dou t of vector D. Therefore the divergence of vector J is equal to minus divergence of dou by dou t of vector D. That's already I have repeated the same equation. That means the divergence of vector J plus the divergence of dou by dou t of vector D, which means I took that negative, that right hand side term to the left hand side, it is equal to 0, right? So one equation we got. Now the divergence is the common term there taken outside the bracket. So divergence of J plus dou by dou t of vector D is equal to 0. So in this expression, the divergence of vector J is not equal to 0, but divergence of J plus dou by dou t of vector D is equal to 0. But divergence of vector J is not 0. Okay, that is equal to 0, which means the term J in Ampere law must be replaced by J plus dou by dou t of vector D. So the term J plus term dou by dou t of vector D, it is known as the displacement current density. Normally the displacement current density is a correction factor in Maxwell's equation that appears in the time varying conditions. That means it is under AC conditions, alternating current conditions, but does not describe any movement of charges, though it has an associated magnetic field. So the theory clearly says that though the name suggests that the displacement current density there is no movement of the charges, but it's purely a correction factor in the Maxwell's equation. Okay, though there is an associated magnetic field, you cannot think of the movement of charges through it. Next topic is Maxwell's equations under static conditions and time varying conditions. And first let me write the expression for Maxwell's equation under static field, that is divergence of vector D is equal to rho v, divergence of vector B is equal to 0, curl of a vector H is equal to J, that is Amperes law, and curl of a vector E is equal to 0. These are the four Maxwell's equation under static conditions. So let me explain briefly about the first equation. Divergence of vector D is equal to rho v, in the sense the total flux through the surface is equal to volume charge enclosed by the surface. That is the meaning. The second condition, divergence of vector B is equal to 0, that is a solenoidal condition. There is no diverging of magnetic field lines from the source. That is a solenoidal case. That is how the divergence of magnetic flux density is 0. The third is curl of a H is equal to J, that is Amperes law, I have already defined. That means curling of a magnetic flux lines or the magnetic field lines around the path is equal to the current density. And the fourth equation is curling of electric vector is equal to 0. There is no chance of curling of electric vectors. These are the four equations under static conditions. Now let us go for the time varying conditions, which means with respect to time varying conditions, how does these Maxwell's equations are going to change. The first and second equation, it is similar. There is no change in the form of the equations. That is divergence of vector D is equal to rho v, and divergence of vector B is equal to 0. But when it comes to the third equation, that is curl of a vector H is equal to J plus dou by dou t of vector D. That is nothing but a modified Amperes law. I have explained about it. And the fourth equation is a curl of a vector E is equal to minus dou by dou t of vector B. That is a Faraday law, even that I have explained. Next topic is Maxwell's equation in integral form. So that same thing we have written in terms of integration, that divergence of vector D, that is nothing but v dot ds. That's a flux density, what I said. That's equal to volume integral of rho v dv, and second is surface integral of b vector B dot vector ds is equal to 0, and third one, the curling H, curling of vector H, that can be written as line integral of vector H dot dl is equal to surface integral of open bracket J plus dou by dou t of vector D dot ds. And fourth equation, curl of a vector E, that can be written as line integral of vector E dot dl, that is equal to minus the surface integral of dou by dou t of vector B dot ds. These are the integral form of Maxwell's equations. Please remember these time varying and time that means static conditions of Maxwell's equations are very, very important one. Next topic is expression for displacement current. When a parallel plate capacitor is connected to a AC source, which is shown in the figure, so let A is the area of the plate and D is the thickness of the plate. Let V is the applied potential of the AC source. V is equal to V naught e power j omega t, where j is the current density, omega is the angular frequency, and t is the time. Let me call this as equation number 1. We have electric flux density, vector D is equal to epsilon into vector E. That's E is the electric vector and D is the electric flux density. Call this as equation number 2. Now when the potential is applied across the plates, there is a development of the electric field. So the developed electric field can be written as E equal to V by D by the definition of the electric field. Let me call it as equation number 3. Now the substitution steps, substitute equation number 3 in 2, so that vector D is equal to epsilon V by D. This is the equation number 4. Now substitute equation number 1 in equation number 4, which means V equal to V naught e power j omega t, that can be substituted in the equation number 4, because equation number 4 is electric vector d, vector d is equal to epsilon by d into V. In place of V, it is V naught e power j omega t, right? So that is called as equation number 5. So vector d, what we got is epsilon V naught e power j omega t by d. Now as we know that displacement current density is dou by dou t of vector d. If id is the displacement current, then displacement current density can be defined as displacement current per unit area. That means that is flowing per unit area. Displacement current flowing per unit area. Therefore, dou by dou t of vector d is equal to id by a. That means area. So in turn, displacement current id is equal to dou by dou t of vector d into a. Therefore, dou by dou t of open bracket epsilon V naught e power j omega t by d into a. I have substituted the value of vector d, that is expression number 5, in the id equation. So id equal to dou by dou t of open bracket epsilon V naught e power j omega t divided by d into vector a. Now take the derivative with respect to time. That will be equal to j omega epsilon a V naught e power j omega t divided by d. This is the expression for displacement current. I will stop here. Thank you.